Hi, I'm Colleen Lewis, and I'm the McGregor-Durand Associate Professor of Computer Science at Harvey Mudd College, and I do computer science education research. Okay, so this is a photograph of the programmers of the ENIAC computer. So this is what programming looked like in the 1940s. What do you think it's going to look like in another 25, 50, or 100 years? And as computer scientists, we'll shape what computer science looks like, but equally important, we'll shape who participates in and benefits from innovation in computer science. And I think CS education research will play a really important role in this. We've seen tons of innovation in CS since the 1940s, and in parallel, CS is such a new discipline that there's huge potential for innovation in CS education. Okay, my research focuses on the broad goal of making computer science more accessible. Towards this goal, I focus on first, understanding and optimizing learning, and second, identifying and removing barriers. In this talk, I'll describe my work in each of these areas and my vision for two recently funded NSF grants. One is related to the topic of learning, and one is related to the topic of barriers. Before that, I'll introduce my current context and background. So I did undergrad at UC Berkeley in electrical engineering and computer science. After that, I worked as a software engineer for both Capgemini, which is a consulting company, and Leapfrog, which makes educational games. Then I returned to Berkeley for grad school, and the program was joint between computer science and education. So I had one advisor from CS and one from education. And based upon the structure of the program, I earned a master's in computer science and a PhD in education. Okay, so after finishing my PhD in 2012, I started a faculty position as a CS professor at Harvey Mudd College. And Harvey Mudd is a STEM-focused liberal arts school with just about 850 students. Okay, I'm excited to tell you about the first theme of my work, which is focused on learning. And I'll keep coming back to this slide to orient you within each theme. Okay, first we'll start with some motivation. This graph is just providing a bit of background and motivation, but it's from a 2020 publication of mine. The College Board provides standardized tests that students can take while in high school to get college credit. You've maybe heard of these. These are referred to as advanced placement or AP courses. And there are 3 such courses, for computer science. The details of these won't be important for the talk, but the growth in AP computer science participation can be seen as a proxy for growth in computer science at the pre-college level. So from about 20,000 test takers as recently as 2011 to 2019, we see almost 160,000 test takers. Short story, there's just a ton of growth here. And the growth in CS learners makes this work of understanding and optimizing learning, for me, really urgent and impactful. And it really isn't just about training computer scientists. All people deserve the opportunity to understand the increasingly computational world around them. And CS has just become a broadly applicable literacy. Okay, so for this learning theme, I'm motivated to focus on that because just like we've seen huge transformation in computer science, CS education is primed for innovation. It's because it's a really young field. And additionally, more students need to learn computer science, which provides urgency for understanding and optimizing learning. Okay, next I'll describe my work and vision related to learning, and we'll come back to the theme of barriers later. Okay, so learning is pretty big. Let me tell you about the 2 open questions within learning that guide my work. Okay, first, what are the foundational concepts that enable computer science expertise? Second, how do students develop this conceptual understanding? And I think it's interesting that we don't have an answer to this first question. We don't know what the principal components are. CS is a young field, which means we have a lot of work to do. And my current path of looking at this started in grad school, so I'll start you there. And in particular, I started looking at programming competence, so narrowing from the broader field of computer science competence or expertise. Okay, so I was inspired by a 2008 paper that analyzed data from 10,000 students who took the AP exam that I mentioned, and And this paper identified the 5 multiple choice questions that were most highly correlated with success on the exam. And I used these questions as interview questions in my dissertation study. That is, I designed a qualitative study to attempt to explain a quantitative pattern. And as a brief aside, in education, we refer to these explanations developed from qualitative data as theories, but it really isn't what we think of as theory in CS. So in education circles, I describe myself as making theoretical contributions. However, I think this education researchy definition of theory is so inconsistent with our definition in CS that I think it's clearest to say I develop models. So as a brief aside, I use qualitative methods to develop models, and these models can be tested with quantitative methods. And when you look for quantitative patterns, you really have to worry about p-hacking. However, the model building qualitative work that I do is intentionally exploratory. Okay, so as I was saying, I use these questions identified from the advanced placement exam as the seed for my qualitative study. So here I have one of the questions from that exam translated into the programming language Racket, which is a dialect of Lisp. For accessibility, I'll read it, and some of you might use the time to answer the question yourself. So the question says, what value is returned by what is it for 4? Then it defines a function, what is it, with parameters x and n. And it says if n is equals 1, it returns x. Otherwise, it returns x multiplied by the result of what is it of x and then n minus 1. And the answer is E, 256. Okay, it computes an exponent. It will just multiply x by itself n times. And this is the work in my dissertation and some follow-up work in 2014, which was funded by the National Science Foundation. One of my PhD advisors encouraged me to write a grant to fund my dissertation, and so my advisors were the co-PIs on the resulting grant. So in this part of my dissertation, I was focused on understanding students' representation when tracing recursive functions. So this shows what a student in an interview wrote in trying to solve the problem we just saw. This might be similar to what you might do if you were tracing the code for each recursive call, and calculating the final answer requires traversing back up the rows to multiply from the bottom to the top 4 by 4 by 4 by 4. Here I've removed the original code from the problem, and above the solid black line is a new example of student work in which each line includes the complete answer, which means that to calculate the final answer, it's not necessary to backtrack through the rows. And this connects to my original point about the open questions in computer science education. So my initial answer is that one of these foundational concepts is program state. And again, within CS expertise, I'm currently focused on programming expertise. And by program state, I mean the values of relevant variables, program counters, etc. And these are things that functional languages have, even though we refer to them as stateless. Okay, so we can imagine that the top representation makes students more likely to get the right answer, although for practical purposes might really be too tedious. And the bottom representation is likely to require a richer understanding of execution stacks, which, depending upon our learning goals, we might want a foreground or background. I think a really important piece of focusing on these representations is thinking about how we can connect it to mathematics. So on the right side, there are calculations shown for a long division problem. Okay, probably no one thinks that the teaching and learning of long division should be an inspiration for CS education or any other thing for that matter. But in long division and math more generally, there are standard and often required ways of showing your work. That certainly isn't true for tracing program state. And I'm not saying it should be, but we definitely need an understanding of the affordances of various written methods of tracing. And that's what some of my earlier work does. A second important thing about long division is that there is a broad agreement among researchers and teachers that students' understanding of long division must be built on a robust understanding of place value. So place value is just the idea of a hundreds, tens, and ones place. And if you want to optimize learning of long division, you need to understand and optimize learning of place value. And I think that connections to other fields of education are an important method for bootstrapping in CS education. So continuing this comparison, there's an infinite number of division problems which all operate on these digits governed by the rules of place value. And there's an infinite number of computer programs which all operate on program state and are governed by semantics. However, before you learn long division, you get a lot of practice with the rules of place value from counting and addition, subtraction, and multiplication. But what are the equivalents for learning about program state? And semantics are likely way more complicated to learn than place value. And so my current and past work is attempting to untangle this concept of program state. For example, in a related project, I looked at young students debugged. And the image shows a brick wall that an 11-year-old student was attempting to make using the programming language Scratch. And in Scratch, if you're not familiar with it, you can direct a character, like the cat shown here, to move across the screen and draw or not draw to make patterns like the brick wall. I analyzed screen recording that included audio of the student debugging. So in an attempt to move the character between the row, the student accidentally traced over a previously drawn line, creating a solid line as shown on the bottom of the slide. And what was interesting was that there was no evidence that the student had any gaps in their understanding of program state. It took them a long time to find the bug, but once they started paying attention to the right aspect of program state, which was the character's orientation before a command to rotate, they fixed the bug in a few seconds. The key challenge in debugging was directing their attention to the right aspect of program state, not their underlying mental model of program state. Oh, and you might notice that there's a 2019 publication listed here as well. So the 2012 paper won the inaugural Best Paper Award at ICER. ICER is the main CS Education Conference, International CS Education Conference. And I was asked to contribute a chapter to the new Cambridge Handbook of Computing Education Research that explained the methods I used in the paper to help people learn to use qualitative methods in CS education. Okay. That's what I've been working on related to learning. And up next, I'll describe my current work and future work related to learning. So I'm continuing this work in a 5-year NSF grant. And in this grant, I'm partnering with an organization called Math for America, or MFA. And they're in the Los Angeles or LA area. And this is a 10-year-old organization based out of the University of Southern California, or USC's School of Education known as Rossier. This program works with public school teachers in the LA area to research and promote innovative math instruction. In my joining this MFA collaboration, MFA is expanding to computer science, excuse me, and I am partnering with high school computer science teachers to research and promote innovative CS instruction. So, for example, I'm working on a paper based upon an interview in which a student attempted to trace sorting code using a written sample array, shown on the top, and using a sticky note version of the array, such that you have to flip the sticky note back to see the value at a particular index. In this data set, the student is abstracting from individual lines of code to reason about higher level state change operations. I think abstraction plays an important role in students learning about program state, and the physical representations of program state seem to provide particular affordances for abstraction, which actually connects to an established body of education research in math. Okay, so probably everyone learned addition and to count by starting with physical objects, like the apple shown here. And we might not even think about learning to count as a process of abstraction. But math education has documented the effectiveness of helping people learn to abstract by using a picture or representation format to bridge between concrete objects, like the apples, and abstract symbols, such as the squiggle on the right that we interpret as 3. And I'm working with high school teachers teaching AP Computer Science in Java, and I've also taught Java at MUD. And from this math research, I had realized that I had the abstract form in my class of Java, the code, and I had the representational form, and that was a written diagram of memory, some sort of memory models, but I didn't have a concrete version. And this slide shows a Java program and the concrete representation before and after the assignment statement A equals B on line 5. And these little plastic pockets can hold a reference, and the little remote control inside are the references that and they have a ribbon to show the referent. One outcome of this work may be innovative teaching, but my goal here is to use these physical items as a way to explore students' understanding of program state. Can these aid in students' abstraction? What role do these play in developing students' understanding of program state? And I've been iteratively designing these, driven by feedback from students and teachers, but ultimately I'll use these in an interview or intervention study. Okay, before I move on to discussing the theme of barriers, I want to describe my vision for my future work related to learning. I'm excited to continue untangling this concept of program state, and I'm expanding my research program could explore CS concepts further removed from programming. I'm particularly excited to explore concepts foundational to security and machine learning because of the increased relevance of these in the daily lives of adults. And although I only describe my qualitative work about learning, my work moving forward will likely involve both qualitative and quantitative analyses. Okay, now let's switch gears and talk about barriers that inhibit access to computer science and computer science education. And I'll start by sharing some data that motivates this work. And this data was aggregated by the Kapor Center for Social Impact. And as a brief disclaimer, the Kapor Center has funded my work. Okay, so the Kapor Center's 2018 report summarized that men earn 82% of bachelor's degrees in CS, while women earn just 18%, and only 20% are Black or Latinx. And as context, 28.4% of the US population identifies as Black and or Latinx. And this is a common term. Latinx is a common term in California, but I'm not sure if people are used to hearing it. And that X avoids the need for the A/O because not everyone identifies as a man or a woman. Additionally, low-income students and students of color are 12 times less likely to have access to CS in their high schools. Here they're using students of color to refer to Black, Latinx, and Native or Indigenous people. And I think this second set of data is helpful because it points us to where we might intervene. Just looking at participation rates, we might assume that women and people of color just aren't interested in computer science. And these data point us to unequal structures of education that should change. So I'm passionate about identifying and removing barriers because barriers currently block access to opportunity. This actually also motivates my focus on learning because ineffective pedagogy can amplify differences in students' access to educational opportunities. And lastly, diversity can drive innovation and help fill jobs. Next, I'll describe my work and vision related to the theme of barriers. And again, I'll start with two open questions that guide my work. First, what structures and cultural barriers limit participation in computer science? And second, what changes enable equitable access to computer science? So interviewing students in an introductory CS class at Berkeley and UW Seattle, this work explored how students made sense of narratives or stereotypes about who can do CS. And we describe a burden that students face when they don't fit. So we hypothesize that for any dimension of the stereotype of a computer scientist that doesn't fit, a student has to do some work to justify that lack of fit. For example, as a white woman, I have to explain why my gender identity, which conflicts with the stereotype of computer scientists as male, doesn't mean I can't do it. Essentially, I need to construct an explanation for why that aspect of the stereotype is a pattern, but not a requirement of the field. This requires that I challenge the pervasive and false stereotype that men are naturally better at computer science. However, as a white person, my race fits with the stereotype of a computer scientist as white or Asian, and I don't have to justify to myself or others that lack of fit. You saw this slide before. There I talked about going from a quantitative pattern on the AP exam that I explored qualitatively. And in this work, I developed a qualitative model, which was then tested in a large quantitative study. So Google commissioned Gallup Incorporated to execute a large-scale data collection, which was published in 2017, based upon that qualitative work that we had done. So next I'll tell you about my 5-year NSF grant focused on barriers, in which I'm partnering with an organization that has expertise in large-scale data collection. So in this grant, I'm working with the Computing Research Association, or CRA, and more specifically, I'm working with the team from the Center for Evaluating the Research Pipeline, or CERP, and the CERP team administers a nationwide survey of undergraduate and graduate students in computing classes, computing majors, and graduate programs. And the focus of our 5-year NSF grant is to analyze this national data set, and we want to drive department-level initiatives related to diversity. And before I dive into this work, I want to get you on board with how important this is for the goals of broadening participation in computing. So, taking a step back, here's a photo of a typical class of mine at Harvey Mudd. This is from the 2016 documentary Code: Debugging the Gender Gap. So Harvey Mudd College is known for having a lot of women in computer science. For example, last year, more than half of our graduating CS majors identified as women. And people always ask me what Harvey Mudd has done to increase the percentage of women studying computer science. And I list off 10 or so things, some of which are cheap and easy, and other of which require commitment and money. And the next thing people inevitably ask me is which of these things had the greatest and least impact. And I don't have a good answer for them. At Harvey Mudd, too many things were changed at once to be able to say. And even if we had great data at Harvey Mudd, there might still be problems replicating the findings in other contexts. The right way to answer their question is to look across institutions. And that's exactly what that CRA dataset allows us to do. That's why I think this research project to drive department-level initiatives for broadening participation in computing is so important. And my work with this CRA actually fits within my existing trajectory of this work. So next we'll return to the work I already told you a bit about based on the interviews from UC Berkeley and UW Seattle. So I already introduced you to this interview study at UC Berkeley and UW Seattle. In addition to the model about students' fit with the stereotype of a computer scientist, an important theme within the interviews was students' experience of competition. So one student mentioned that even my professor told us that some people are just born that way, with that mental outlook that is compatible with CS. They feel it's so easy for them. Yeah, and he told the rest of the people that some of you will try, but some of you won't get it. And it's just that your mental outlook isn't made that way. It's something you're born with. You can't help it. So the idea that CS requires innate ability is an idea referred to as a fixed mindset. And an environment where students compete to be able to study computer science may reinforce ideas about CS requiring innate ability. And actually, regardless of what you think about CS ability, you do not want students to have a fixed mindset, because students with a fixed mindset are less likely to persist in the face of challenge. That's not going to be helpful to them. Okay, so one more quote. Another student explained that CS1, so that's an introductory CS course, is like taking a foreign language class, but the majority of students are already native speakers. You'd think that helped you, but teachers adjust to the native speakers, so people who are new to the idea get left behind in the dust. Having a mix of experiences in an introductory course may intimidate students without experience, and also may lead to poor instruction if, like the student believes, the instructor assumes background knowledge that only students with high school experience have. Okay, now we're going to dive into the research question using that Computing Research Association data set. That's the survey, the multi-institutional survey. So in this study, we focused on department policies. In particular, we were focused on first-year students because we thought department policies might be most impactful for students considering a CS major. And our study included 1,245 first-year students who had taken a computer science or computing course. And it appears to be increasingly common that institutions are adopting competitive enrollment processes to limit enrollment in the CS major. So based upon my previous research, I was really worried about the potential consequences for this. And our study included 80 institutions, and we looked up whether or not they had a competitive enrollment process or policies that required competition to get into the major. We also looked at whether these institutions allowed students to use prior experience to pass out of CS1. And we separated students who did and did not have high school experience in our analysis, and we looked to see if these department policies predicted a perception of the department as unwelcoming, a lower sense of belonging, which is an important predictor of performance and retention, lower self-efficacy, which self-efficacy is a belief in your ability to do something, and a fixed mindset, which we just talked about related to innate ability. So we realized CS1 enrollment policies were a little trickier than we originally expected, and we realized this after pre-registering our study. So returning to the case of UW Seattle, it was they actually allowed students to skip CS1 with prior experience, but people often didn't because getting an A in CS1 could help them get into the CS major. Okay, so our analysis will actually not include the CS enrollment policy because that one actually is a good bit trickier than we had initially hoped. Okay, so among first-year students, do competitive department policies for major declaration predict these 4 things? And consistent with our hypotheses, it did predict the department as unwelcoming, a lower sense of belonging, and a lower self-efficacy. And these 3 values were the only ones in the linear model that were statistically significant at the 5% level. And these patterns were not statistically significant for a fixed mindset, which again, upon reflection, makes sense since they might be less impacted by the environment than these other measures. Filling in the rest of the numbers, I already mentioned that fixed mindset wasn't particularly interesting, and these other 5 yeses indicated that competitive enrollment policies were bad for students, or predicted, the department is unwelcoming, a lower sense of belonging, and a lower self-efficacy. And this isn't statistically significant, but we see that for students with high school CS experience, competitive enrollment predicts a higher sense of belonging. That's what the bold no means. If not everyone gets to be a CS major, and you come in with CS experience, you might expect to win at the competition, which could increase that student's sense of belonging. Okay, 2 more things I want to note. First, all these results are controlling for gender and race. And second, although this paper won the best SIGC research paper this year, we're already working on building on this paper with a more accurate characterization of department competition because here we used a really conservative process for classifying departments as competitive. Okay, that was basically a paper in 1 slide, and we'll move on to a second study that I'll share with you, and I'll condense that one into 2 slides. Okay, as promised, we're going to dive right in. A perception of computing as having communal affordances was a significant positive predictor of sense of belonging. And sense of belonging, I already mentioned that was a really important predictor for retention and performance. And then communal affordances, that's a student's perception of computing as allowing them to pursue communal goals. And communal goals are focused on working with and to the benefit of others. These are contrasted with agentic goals, which are more focused on individual advancement. Okay, again, communal goals involves the desire to work with and to the benefit of others. And communal goals are particularly interesting in the STEM context because people from groups frequently identified as underrepresented in computing are more likely to endorse communal goals. For example, Black people, Latinx people, and Asian people are more likely to endorse communal goals than white people. Women are more likely to endorse communal goals than men. And first-generation college students, that's students who don't have a parent or guardian who have completed a 4-year college degree. So first-generation college students are more likely than continuing generations college students to endorse communal goals. So there are different patterns of communal and goal endorsement. And we found that believing that computing will allow you to pursue communal goals predicts a higher sense of belonging in computing. We also found that a match between a student's goals and a perception of computing as having communal affordances was a significant positive predictor of sense of belonging. That is, this match between wanting to pursue communal goals and perceiving computing as having communal affordances for pursuing those communal goals predicts a higher sense of belonging. And these patterns were statistically significant when controlling for race, gender, first-generation college status, and institution. And our sample was almost 6,000 CS majors across 183 institutions. And I promised you 2 slides in that, and in this second slide, we'll try to visualize these results. So here we see a sense of belonging on the y-axis and perceived communal affordances of computing on the x-axis. And these are all mean-centered and standardized. So 0.2 means that's 0.2 standard deviations above the mean. And here we have a third dimension in our linear model, which is students' communal goal orientation. To visualize this third component, communal orientation, or those communal goals, we'll collapse and just look at the predicted points, 1 standard deviation below the mean and 1 standard deviation above the mean for communal orientation. So here we see these two lines plotted. Sorry, they're not parallel. For students with low, that's the one on the top, communal orientations, and high communal orientations, perceiving communal affordances of computing predicts a higher sense of belonging. That's based upon the positive slope of both lines. Our statistical test uses an interaction term, which is essentially checking to see if these 2 lines have different slopes, and they do. And the p-value is less than 0.001 for that interaction term. And our results suggest that convincing students that computing has communal affordances is better for everyone. Again, that's the positive slope of both lines, and can have a differential impact for women, students of color, and first-generation college students, because such students are more likely to endorse communal goals. And I think looking across institutions, here 183 institutions, is really important for identifying effective strategies for broadening participation in computing. Okay, let's pop back to the open question related to barriers. So the thing is, there's actually already a good bit we know about these things. And in my first NSF grant at Harvey Mudd, I sought to disseminate such information. So in this project, csteachingtips.org, the goal of the project was to document and disseminate effective teaching practices. So here I interviewed 150 computer science teachers and developed a website with 1,300 tips for teaching computer science. And this work to document knowledge about the teaching and learning of computer science is important for advancing computer science education research. That's the intellectual meat and the intellectual merit. However, the work of disseminating these tips to CS teachers is about the broader impacts of the work. Okay, stepping back, I think this slide sums up my long-term goals perfectly. For me, everything is driven by my goal to make CS more accessible, and I think this requires a focus on learning and barriers. I'd like to acknowledge the funders that have supported the work I discussed here. I'll end on this slide, which shows the 2 themes and 4 open questions that drive my work. Thank you for your interest in my work.